Good morning, everybody. So today we have the pleasure to receive Dr. Federica Bianco from New York University. So this is the second webinar of our LSST series, and today she's going to talk about the transient sky. So thanks a lot for accepting this invitation. Please go
Of
ahead.
course. It's my pleasure. Hi, everybody. Can everybody hear me okay? I'm going to assume that if I don't hear protests, you can hear me and you can see the slides all right. So my name is Federica Bianco. I work at NYU, and I am the co-chair with Ashish Mahabal of the Transient and Variable Star Collaboration of LSST. I became the co-chair about just a little longer than a year ago. And I will talk to you about LSST in the context of the transient sky discovery and transient sky understanding, to tell you what LSST can do for this particular branch of astrophysical science, which I think is. And then I will talk a little bit about our collaboration, the structure of it, and what we are working on currently. Of course, you know about LSST, and you had Lucien, who's excellent, I'm sure cover all of this, but just very briefly to put it in context, LSST is going to be the largest survey which is designed for the future of astronomy, the larger in terms of, certainly in terms of investment, at least for ground surveys, and definitely in terms of the number of people that LSST is trying to put together for the project. It's an enormous collaboration that is already including the work of a very large number of people. The telescope itself, LSST stands for the Large Synoptic Survey Telescope. So it is a telescope and a survey. The telescope is designed to conduct a 10-year survey of the sky. And of course, it's going to be in the Atacama Desert in Chile, and it's under construction as we speak. And the telescope is quite amusing because it's shaped rather funny compared to most telescopes that people are accustomed to seeing. So I enjoy showing the slides in which the telescopes look super chubby and stocky compared to you know, the long and elegant telescopes that you see, the Gemini or something comparable to that. The design is very peculiar, and it allows LSST to work rather differently than traditional telescopes, in fact. The effective aperture is 6.7 meters. The size of the telescope is in excess of 8 meters. It has a stunning field of view of 9.6 square degrees. And something that synoptic surveys, I'll explain what I mean by synoptic surveys in a second, but something that synoptic surveys like to quote is the entendu of the survey, which is what is the collecting area of the surveys multiplied by. And for LSST design is specifically targeted to maximize the entendu of the telescope. The survey is going to be conducted with the mantra of deep, wide, deep, and fast. Wide, deep, and fast basically means that LSST is not going to compromise on any aspects of the survey. It's going to be a wide survey, so it will cover large chunks of sky. It will cover nearly all of the southern sky and as much of the northern skies as it's visible from Chile, and it will cover it over and over a few days interval. It will be deep, so it will access very faint magnitudes, magnitudes that go as faint as 27th, which is really faint for ground-based surveys. And it will do that in a short amount of time, so that it can repeat the imaging of the entire visible sky at an interval of a few days. The sort of common notion is that it will take a complete movie of the southern sky every 3 days. This is not technically true in the sense that the details of the cadence will determine how often the entire sky will be visible and whether it will be visible and the entirety of it will be visible repeatedly at a short cadence. And the design of the details of the survey, the design of the cadence is in progress right now. The survey is designed itself to last about 10 years, and I have a nominal start time year of 2022 to 2032, The commissioning should start earlier than that, so around 2018, and the survey may start a little earlier than 2022. And of course, the telescope will exist past the 10 years of the survey, and it's a good question that doesn't have an answer yet. What will we do with this telescope? But the nominal survey will last for 10 years. Again, the wide, deep, and fast is achievable through innovative technology, particularly innovative optical design for the telescope. So when you look at a telescope that is comparable in size and diameter, an 8-meter telescope, for example, you can think of Gemini South. And obviously the look of the telescope dome, of the telescope structure, and of the mirror itself is very, very different from what you see with LSST. Particularly the mirror, these are both mirrors that refractive, and they have the secondary in the center of the primary, so they have a hole in the center of the primary, which is the little circle that you see in the middle of my slides. But this hole is particularly large for LSST, which is the reason why we go from an 8.4 meter diameter to a 6.7 effective diameter for the telescope. So the design of the mirror is what allows us to observe a really, really large field of view. And on the right side of this slide, you have a comparison of the field of view of Gemini, which of course is designed for spectroscopy. So it has a very narrow field of view by construction, but with the stunning field of view at the bottom of LSST, which is 9.6 square degrees, and you can fit many, many moons into a single image of LSST sky. The large hole in the center allows LSST to host a dramatically large camera. This is a model, a 3D rendition of the camera with a person next to it for size comparison. So this is really a terrific instrument in both technology and size. And just for reference, it's a 3.2 gigapixel camera, so 3.2 billion pixels. And this is how many iPhone 6s it would take you to pan a field of view that would have as many pixels as the LSST camera. But what is really special about LSST and what really resonates with my scientific interests is the incredible amount of data that LSST will produce. So the data stream of LSST will truly be unprecedented. LSST will deliver 30 terabytes of data every night. 30 terabytes of data is 1 million trees made into printed paper. There's a tremendous amount of information that can be exchanged in 30 terabytes of data. And of course, LSST aims at subscribing to an open data and open science policy. So all of the data that LSST will generate will actually be available to the entire world, perhaps at different times, and really truly the metadata, the data that goes with the images, and the process data may be available to different sections of the audience at different times. But LSST is organized in such that really the majority of the data can be completely open access, which is commendable, but also which takes a large effort and really pushes the boundaries of the data technology that we have at this time. For example, imagine that they have to transfer 30 terabytes of data from Chile to the United States, where the data gets processed in real time. So it would take 67 hours with a 1 gigapixel per second connection, which is not a terribly bad connection. And of course, if we want to talk about the transient sky, if we want to talk about things that change in the sky, then that is a prohibitive amount of time. We cannot afford to find out that something has exploded in the sky days after that, because we lose a tremendous amount of information about what happened if we lose the very first hours and the very first days of the transient. So in order to transfer that amount of data, in fact, LSST will use dedicated pipes, dedicated long-haul networks, which are going to be running down the coast of the Americas from Chile to the United States. So I cannot stress too much how critical it is to get information about transients in as short a time as possible. When we do transient science, when we study, for example, supernovae or GRBs, or even variable stars, variable objects, but specifically when we talk about transients, and here the difference between variables and transients, generally speaking, I'm going to refer to variables as things that have variability patterns that repeat more or less identically, so they can be periodic or they can have stochastic variability, but they are objects that are known to continuously change, as opposed to transients that are objects that suffer maybe even a single change. Just imagine a supernova explosion. And so specifically for the transient sky, it's really critical that we find out about the transients, essentially in real time, so that we can organize the study of the observational study of the transients. We can start looking at the transients the way that allows us to obtain the most information out of it, which means, which can mean a number of things, from just continuing to monitoring with LSST without changing the cadence of LSST, or perhaps having targets of opportunity with LSST where the cadence can be tweaked to follow really important transients. This could be an option, for example, for gravitational wave discoveries, counterpart of gravitational waves, or simply just designing the follow-up strategy with other telescopes, with spectroscopic surveys, or with telescopes from space. But we need to know about the transients really, really fast in order to be able to organize this follow-up campaign optimally. And so the promise that the LSST data management team is making is to deliver information about every source in the image within 60 seconds of when the image is taken. And that is a really tremendous, tremendous task. So the data management team likes to show this slide of the workflow, basically what they have to do when they get an image. So if you look at it, I don't know if you can see my mouse, but if you look at it at the top, each one of these color trapezoids represents an image that gets taken. And in fact, 2 images are taken every 30 seconds. Image integration for LSST is actually 15 seconds, but you require 2 images to just remove the cosmic rays that contaminate the image and would look like transients if we were to analyze the image. But in reality, they're not transients. They're just high energy rays that hit the camera but don't have to do with the background sky, for the most part. So each pair of images, visit 1, snap 0, and visit 1, snap 1, constitutes what I'm going to refer to as an image for LSST. And one of these sets gets produced every 30 seconds. It gets transferred, and then the team has allowed 60 seconds to deliver the alerts to the community. What are the alerts? It means to deliver a list of all the things that in the images have changed from a reference image of the same portion of the sky. So basically, what are the transients in the sky, in this patch of sky? They have 60 seconds to do them, and they expect to detect millions of these of transients events. They expect to detect thousands of supernovae per night, whereas today the rate at which we discover supernovae is maybe 1 every few days. So this is really a tremendous task. And so instead of showing this slide the way I like to put it in context, and I don't think you're going to let me get out of this presentation and show you another presentation. So really, I think a more representative view of the task that the data management team has at hand. More like this one. This is not working very well. I'm sorry. Yep, I don't know if you can see the video, but the idea is, this is basically what they're trying to do. An image every 60 seconds, and they have to take a difference from a reference image of the same sky to remove everything that is constant and be able to see the things that have changed. They have to classify, at least minimally, the things that have changed so that they can be directed to different people. For example, we want to identify solar system objects. Those change because they move across the plane of the image. But that's a very different type of change than a supernova explosion. So we want to identify moving objects in the image within those 60 seconds, produce a catalog of those and match them with known moving objects so that we can identify those that are new discoveries. And we want to identify all the other changing objects in the sky. So this is a task that this is going to be achieved by the data management team, by the LSST team itself, of which I'm not part. But I am part of the community that will receive these catalogs. So once they construct these catalogs, which again, every 60 seconds will have thousands and thousands of images, then the catalogs will go to brokers, and a number of people are working on that aspect. The brokers will take the entire catalog of images with all the information about that pixel, about that location in the sky in the past, for all the images that existed that were taken by LSST, and will classify them and distribute them to the community according to the classification. For example, I do supernova science. I only want classifications that have to do with supernovae. Perhaps I can choose and fine-tune the parameters of these classifications such that I maybe want only high probability supernovae, or anything that has a reasonable probability of being a supernova. And whereas my variable star friends are going to want to know about, for example, pulsating variables that are going under eruptions, and they do not want to know about supernovas. So that task will be done separately from the LSST team by brokers, and there will be a few brokers throughout the United States, a few brokers throughout Europe that will distribute the alerts. So that enables people in the transients and variable stars community to use their time, both their person time and their telescope time, to go after these transients. So as a supernova person, I will have an allocation of a certain number of hours at, for example, telescopes that are able to do spectroscopy. And once I get my alerts, I will decide whether I want to ask for a spectroscopic follow-up of the transient. So that's sort of the idea and the plan for the transient sky with LSST. Let me go through the numbers a little bit again. So we expect 1 to 10 million time domain events per night. So thousands of time domain events, and again, time domain events means both variables and transients in this context. Thousands per image. These will be detected and transmitted within 60 seconds of the LSST observation. LSST will also provide a catalog of 6 million bodies in the solar system with orbits, multiplying by orders of magnitude the number of solar system objects with known orbits as of today, simply because it will go much deeper and it will have a very regular cadence for 10 years. It will produce a catalog of 37 billion objects, which includes 20 billion galaxies and 70 billion stars. These are static objects, so objects that do not change. But because LSST observes the sky over and over again, it can make stacks of the sky that go to a very, very large depth. And also, it has a very good spatial resolution, so that we can distinguish stars in high crowded regions and shapes of galaxies. So those objects will be characterized in shape, in color, and in variability where they are variable. And the deep sky, the deep stacks that I was talking about, the fact that we can co-add the images for the same patch of sky that we take over 10 years, allow us to go to a very significant depth at a very high spatial resolution, which allows to do things like measuring weak lensing, but also is important in the context of the transients because we're going to be able to resolve the progenitors of transients. For example, where now we don't see stars, where supernova or luminous blue variables explode, we will be able to see them with LSST, of course, under some circumstances. The science drivers for LSST are dark energy and dark matter, exploding transients in variable universe, and studying the structure of the Milky Way galaxy and its neighbors, so stellar with resolved stellar population, and an inventory of the solar system. While only one of these is specifically talking about transients and variables, in fact, 3 at least out of these topics do have to do with the transient and variable sky. And in fact, the solar system is also it also has to do with the transient and variable universe, because solar system bodies move and therefore they change. Our view of them changes in the plane of the sky. But let me focus on the top 3, because the solar system collaboration is separated from ours, and it has its own team that I'm sure we'll talk to you soon. So dark energy and dark matter is very relevant to transients, because one of the main probes of the universe, of the shape of the universe and of the evolution of the universe, are supernovae. As you know, supernovae won a Nobel Prize precisely for discovering the fact that for discovering dark energy, the fact that the universe is not only expanding, but expanding at an accelerated rate. So transient science, in the sense of supernova, is deeply connected to dark energy and dark matter. Of course, dark energy and dark matter investigations also use galaxy clusters, large-scale weak lensing, large-scale structure, baryonic acoustic oscillations. But supernova are at the heart of this as well. Of course, exploring the transients and variable sky is all about the transients and variable sky, but also studying the population of the Milky Way galaxy is really relevant to transients and to the transients and variable universe, because if we study the population of relatively nearby stars, then we can identify the transients before they happen, or relate them to what was in that location before the transient itself happened. Which means we can identify the progenitors, for example, of supernova. And the progenitor of supernova is really an open question to a large extent, is an open question in science, in astrophysics and transient science. So the survey strategy has a number of LSST will conduct a number of different surveys, which will be different in the sense that the cadence of the surveys will be different. The wide, fast, deep survey, which is the core survey of LSST, which fulfills the requirement that I mentioned earlier of being wide, fast, and deep, will take about 85% of the observing time at LSST. And right now it's designed to collect pairs of images. So 2 pairs of those 30 seconds images that are themselves made of 2 images per night. We need 2 pairs because that allows LSST to identify moving objects. So again, for the solar system objects, so that we can see that something that has changed in the image has not changed because it's a new object, but because it's an old object that moved. And if we have 2 images at least, and this may actually end up being 3, we refer to these as doublets or triplets, then we can design an orbit that would fit those 2 positions that we have, and identify whether we already know the object, or whether it's a new object, or even whether it's an object that is in a particularly interesting orbit worth studying with other telescopes. So this will be 85% of the observing time, so we want to exploit this for the transients and variable studies as well. However, there are surveys that are also targeted more narrowly to study the transient sky, and particularly the deep drilling fields. There is a subset of fields that are 5 to 10 fields that will be observed more, will be observed on occasional nights, more in depth, so that we get more than 2 images per night, but we get maybe 10 images, and we get images in all filters, so that on the same night we have information about the color of things that change in that patch of sky and the variability of things that change in that patch of sky with more than 2 data points, so that we can understand the shape of the variation. And there's also other surveys, the galactic plane, the south celestial cap, and the northern ecliptic. And a case for these surveys being relevant to transient sky can be made, of course. We are but one of maybe 10 science collaborations, and I know you've heard about the science collaborations from Lucienne a couple of weeks ago, where the transients and variable stars. I co-chair the collaboration with Ashish Mahabal, who's been the co-chair prior to me with Lucienne for several years. The collaboration focuses on the transient sky, and the transient sky itself includes a very large and diverse range of phenomena. It includes phenomena that are that are diverse physically, for example, from explosions to geometric transients, planetary transients. We consider variability in variables and transient objects all planetary transits, because they do change. Even though the objects don't change intrinsically, they do change in our image. What we detect is a magnitude or brightness change. So the phenomenology is very different. The time scales are very different. The time scale for a transient is at best hours. The time scale for a supernova explosion, depending on what details of the supernova explosion you're interested in, can be days, or even for the entire duration of the phenomenon is months. We have transients like Eta Carinae, like great eruptions that last for years and decades. So truly we go from minute timescale changes to the longest timescale changes of decades, and all of those fall under the umbrella of the transients and variable stars and are under study for our collaboration. Because we work with such diverse phenomena, we are separated internally into subgroups. And here you have a list of the currently 15 subgroups in our collaboration. And as you see, some of these refer to the kind of transients they are studying. For example, there is a supernova subgroup, or a tidal disruption event subgroup, or an interactive binary subgroup. But some of these refer to what you actually want to do with the transients and variable star. For example, there is a cosmological subgroup, or a classification and characterization subgroup. So all members are affiliated with at least one subgroup, and we have nearly 160 members, of which truly not all are active, of course, but we have a few tens of people that are actively working within our collaboration. So each person, as they enroll in our collaboration, chooses a primary affiliation, so that will be the main interest, the main transients and variable interest that most closely relates to their science expertise and interests, and up to 3 secondary affiliations. And let me show you a little histogram. So we have a lot. See, this is the histogram just of the primary affiliations, and again, people can be with the secondary affiliation can be related to more than one group, but we're dominated at this time by the supernova subgroup. And the reason for that is that there was a dedicated supernova group, one of the reasons anyways, there was a dedicated supernova group within LSST, that collaboration within LSST that just got dismantled a few months back, and we embraced a lot of the members of that collaboration as transients variable stars members, and also perhaps the fact that I, as the co-chair, supernova is much of the science that I do, so perhaps my connections are actually fostering that subgroup more than others. But we have a large number of people interested in just classification and characterization. That subgroup has links with the statistics, astrostatistics subgroup that are very closely related. Classification and characterization, particular classification, is a huge problem in astrostatistics and machine learning, a very interesting problem in machine learning. And again, some of these are on the transient side, and some of these are on the variable side of things. And so, like all the other collaboration, what we are trying to do, what we're tasked with at this time, is helping the road mapping of LSST. How can we design the best survey with the LSST instrumentation and capabilities that allows us to learn the most about the universe? And of course, because transients and variable phenomena are so different, many phenomena within the transients that are of interest to the transients and variable stars collaboration will benefit from different and sometimes very different and sometimes completely orthogonal observing strategies. So our task is to put together, to collectively understand what survey strategies, which means what cadences, how many times do you go back to the same field, what filters do you go back to the same field with, how many times do you image a field in R versus U, to understand which one, what's the strategy, what strategy benefits, what kind of transient study, and to put together this information to maximize the study of the transient universe as a whole. And this is a very, very hard task, which brings me to the reason why I got nominated to be the LSST chair, which I thought was because of my scientific expertise. But in fact, I think it's because they just wanted somebody to really shake people up. And you may find amusing that in my second job, I'm actually a professional boxer. So I think that actually is why I got nominated to be the co-chair, because I can threaten and intimidate people into working with us. So the time for doing this, the timeline for this is actually very short. The time that we have for LSST to decide what cadence it will have, what the details of the cadence are, is really in the next couple of years. And it's very hard to convince people to work on this right now, because although this is a timely task that has to be decided in the next couple of years, the products of LSST are just short of a decade forward, maybe more like 5 years forward. So it's hard to convince people to work on something that will eventually be fruitful in about 5 years. But this is the really critical time, the really crucial time to make sure that LSST makes the right decision to maximize the study of the transient universe. And this is how I plan on convincing people to do that. So again, the transients and variable stars, the transients and variable star studies are going to be made or broken by the cadence choices that LSST is going to make. So I'm going to take you through a few examples of what we have understood about the current cadence choices, the current proposed cadences, and how we're trying to maximize maximize the understanding of the effects of cadence on the transient universe. And I think I will talk for another maybe 7 to 10 minutes, and then I hope to open the floor for questions and make it more interactive. So among the efforts that we've made to understand how to design the best transient and variable survey within LSST, we just had a collaboration road mapping meeting that produced roadmaps. The roadmaps you can find on our website. Some of them are still in the making. Most of them are just drafted, and they're continuously living documents. If you see anything, and if you want to contribute, and if you want to give suggestions, you're very welcome to. We have also been working on the Observing Strategy white paper that I know Lucian has mentioned in her discussion, in her introduction of LSST science collaborations. This is a living document that is being co-authored by a very large number of people in the astronomical community. Most of these people fall at least under one or more collaborations. A lot of them fall in our collaboration, and our collaboration is writing 2 chapters, which I think in the current version of the document are chapter 5 and 6. Chapter 5 for the variables and chapter 6 for the transients. And you have a couple of links here where you can see both a static copy of the current version of the document, but more interestingly, a link to the GitHub repository where things are being developed, where you can see the actual work in progress. And so in order to contribute to this document, some technical expertise are required. The LSST collaboration, the LSST team, sorry, not the collaboration, has produced an excellent tool to help us understand the effect of cadence choices of LSST. So they produced the OPSIN, which is a simulation of the sky as it would be seen by LSST. This was produced under Andy Connolly's leadership, and the OPSIN is complete now for the version 1 of the OPSIN is complete, and it's been in use for some time, maybe upwards of a year, and they're continuously producing better versions of that. So a better version of OPSIN is to be released imminently. And so what that tells you is basically it's a simulation of the entire sky with known objects in it, and it tells you how LSST would see them at any point, would see that portion of the sky at any point in time. And they've also produced the MAP, the metric analysis framework, which is a set of Python codes that interacts with the OpSync to tell you, given a particular cadence, this is the information that you will get about this phenomenon or about this portion of the sky. So using these two things together, we can vet a particular cadence proposal and see how it affects a science case within the transient universe. For the transient specifically, there are a number of metrics. So, and by metric here I mean things that are designed to measure how well one can answer a particular science question. A number of metrics that are designed specifically for the transient universe. For example, this is the supernova alert fraction. And every time I show you something like this, on the left you see a map of how successful that metric is at a particular point in time over the course of the survey. And on the right side, I'm showing you a histogram that tells you how many supernovae would be detected and within some constraints, and the constraints in this case are detection before peak magnitudes in any filter, and you could be you can be pickier and choose more tightening constraints, of course, and decrease this number. But this is the fraction of supernovae that will be discovered by LSST. Because transients and variables, of course, rely on seeing the same portion of sky multiple times, and particularly to see it at multiple times during the duration of the transients, when the transient is at different magnitudes. Very at the heart of our understanding of how well LSST can do is the understanding of what is the gap between two images. So if you happen to be a transient scientist or a variable scientist and you have a particular phenomenon of interest, then we produce intra-gap and intranight and internight gap statistics for a number of proposed cadences that can just give you the first idea of, am I going to be able to detect my transient? So for example, if your variability is of the order of a day, then you may not be able to detect it unless your observations are staggered throughout the day. So these are just some of the plots, the kind of plots that we make to understand how the cadences affect transient science. And again, every time I show you one of these plots, what you see here with the names of Minion, Enigma, Kraken, and Minion 1020, those are different proposed strategies, different proposed cadences. So for example, you can see that the Kraken cadence has a much smaller media intranight gap, which means we see things in any filter. If you are interested in seeing things in any filter, you are going to be able to see them at a shorter interval. So that's good, for example, for faster transients. So the transient universe as a whole covers a very large breadth of the parameter space. So we transient scientists like to put this in a phase space of the transient, to put this in the context of the phase space of the transient sky, where on the y-axis you have the luminosity of the transient, and on the x-axis you have the characteristic time scale of the transient. And so this is a version of the transient sky as we know it right now. Particularly notice the gap at the bottom left of this plot, where we have characteristic time scales shorter than a day and relatively faint magnitudes. The gap there is not there because there's nothing interesting happening in the sky. There's nothing there because right now our surveys are not designed well enough to probe that region of the space. And we hope that LSST will change this. We hope that LSST will discover a large number of phenomena that have variability times that are within a day and that are not accessible to transient surveys right now. If you're thinking about this in the way that I'm describing, it should be intuitive that not only the cadence matter, but the detail, not only the cadence in terms of what is the gap, what is the time that passes between two observations, but also what do you decide to go back to the same field with. what filter are you going to observe with? Are you going to do a survey that covers all of the sky in R and then goes back to the same sky in G? So if you do that, then the time that passes between your R images and your G images is going to be days. So you're effectively not going to have color information for transients that happen on timescales shorter than days, which means if the transient changes a lot within a few days, like a supernova does, then having two different filters at a separation larger than 24 hours is really not allowing you to know the color of the transient. And so normally, the way we understand transients, if we don't have spectra, but spectra are just very refined colors. So really, we understand transients by two metrics. What is the shape of the change? So the light curve, which means ideally we would like LSST to look at the sky in the same filter as often as possible to get a detailed light curve of transient. But also, what is the color? Is this a blue transient or a red transient? Because the color tells us really a lot about the physics. If it's an explosion, it's likely to be blue. And if you do not get multiple filter observations within ideally the same night, you do not have that information. So there is a tension even within the transient studies between color and sampling, because you cannot sample a light curve in a single band finally and also get the color within LSST if you want to be able to image the entire sky every 3 or a few days. So if you want to fulfill the requirements of the wide, deep, and fast survey. And that's the reason why some of the fields are designed to be observed with different strategies, the deep prelim fields. And just to put it in context, when we talk about variable stars, we have variable objects. There's a very large number of variabilities. We have a couple of tables in the chapters that show the variability amplitude and time scale. As you can see, even variable stars change on time scales between minutes and weeks. And this doesn't include the planetary transits, which are also of interest to the variable stars community. They're also included in the umbrella, in the variable objects umbrella. A couple of things that we have designed for the study, for understanding how well LSST studies the variable sky. This is a variability depth map, which shows you, given a certain cadence, how deep can you detect variability. Can you detect objects that change at a magnitude of around 20, which is really faint. We don't know a lot of objects that are variable at those magnitudes right now because our surveys are not that deep. Another thing that you can ask, for example, is how well you recover a variability period if you have a periodic variable. And so chief periodic variables will be, in fact, planetary transits. And so different strategy will allow you to detect the periodicity and to characterize the periodicity better than others. And also that depends on the shape of the light curve. So under certain strategies, we will be able to understand what the period of something that we see varying is. And so in this kind of plots, when you see something along the diagonal line, that means you got the right period. But there are, depending on the shape and on the observing strategy, there are a number of things that will be mischaracterized because of aliasing, because the period at which you observe, you go back to the same field, is some multiple of the period of the object. For the eruptive transients, we also have a very large number of phenomena, and look here at the event timescales. They go from minutes for flaring stars to really decades for things like LBVs. We have weeks to years, but different types of LBVs will be can vary on timescales of years or decades. And also something that is very popular and of great interest right now is LIGO detection, detecting electromagnetic counterparts of gravitational waves. That is something that falls under the umbrella of the transient studies, and it's considered under a group, and it's something of something that is very popular now and very interesting. And also we left space for unknown, because we know that there are a lot of things that are changing in the sky that we were just unable to discover yet because of how we designed surveys until now. And a number of questions. Can I understand transients through after the survey runs for 6 months, for 6 years, the entire, a lot of studies that can be done on samples statistically, so that even if each individual object in the sample is not studied at a very high cadence, you can put together the classes of objects and understand and characterize transients, specific transients. For example, I conducted a study that looked at what are whether we can see what the progenitor of supernova type 1a are from the shape of the light curve. And I conducted this study on 3 years of supernova legacy survey. There was a similar study on 5 years of SDSS data. LSST can achieve the same result that I obtained on 3 years of SNLS data in about 3 months. So for this kind of survey, LSST can truly be phenomenal. We don't have to go through the details, but but these are non-time critical tasks that we can answer on an ensemble of objects. But there are very time-critical tasks, such as classification of characterization, detection of fast transients, detection of counterparts or GRBs and gravitational waves. If we don't discover those right away and understand what they are right away, we're not going to be able to do science with those. And again, here is a matter of tension between color and sampling. We try to evaluate what is the ideal cadence to at least being able to see if something that has changed is a new transient. If something that changes is new, then the shape of the transient is going to be very steep. Typically, transient change very rapidly at the beginning and then slower at later days. So we created some confusion matrices that tell us, given the gap between observations, how well can we see, can we understand what these objects are. And right now, I want to tell you that the LSST cadence is designed to mostly try to collect the pairs of objects, the doublets that we talked about, within maybe half an hour, maybe an hour. When you see the confusion matrix at the bottom being white, that means you're very confused. You're not able to separate different types of transients. You're not able to separate the time scale, the age of the transient. To actually separate and understand transients, what transients are, optimally you would have data points that are separated by maybe 24 hours. But at that point, you have lost the beginning of the transient. So ideally, LSST will be able to push the doublet, the couple of images that you see, to a few hours to maximize our ability to understand what things are, but also our ability to go after them at early times. The last thing I'm going to show you is a couple of slides on how supernova will look like from LSST. LSST will detect, as I showed you, and discover a very large number of supernova. And supernova are the heart of cosmology because we do supernova type 1a. We observe the expansion of the universe. We measure the expansion of the universe at different redshifts with the shape of supernova type 1a's. So these, however, are the kind of course, the underlying curve is the model, is what the true variability of a supernova type 1a is. And on top of that, you have the data point for some simulated LSST surveys. And the data points have very large error bars and are quite sparsely sampled. So we can do supernova type 1a cosmology with this, but right now the design of the survey is not optimized to do this. There is a question of whether supernova cosmology will truly benefit from LSST wide deep field survey, wide deep fast survey, and not only from the deep drilling fields. We are setting up a transients classification challenge. One such challenge was done in 2009 for supernovae. But again, one of our main goals is to understand how well can we understand what transients are so that we can design the follow-up with the given LSST strategy. The supernova transient challenge was in 2009. A lot of things have changed since 2009. For example, our machine learning skills, our understanding, the machine learning field in the sense of like how machines understand things that we maybe don't even understand has improved dramatically. And if Google can find cats in videos without requiring really essentially any metadata, we should figure out how well can we understand what how well can a machine understand what transients are compared to ads. So we're working closely with the statistical and astrostatistics collaboration for this. There's a number of people that are working on this, both on the classification itself and on the collection of known objects like curves that will allow us to do the challenge. So the challenge, we hope, will be issued in the next year or so. We also have improved our knowledge of different types of objects dramatically in preparation of LSST, so we plan on including a lot of different transients in this challenge that were never included in similar challenges before. And I think that's really all I wanted to tell you. Our collaboration is, of course, open to accepting new members, so if you're interested, please contact us. And talk to me or Ashish. And I think I want to open the floor for questions.
Okay, thank you very much for your talk. So, have time for questions.
Was a little long, I'm sorry.
No, it's great. So, questions? So maybe let me start. How are you going to deal with the unknown?
So that's fantastic. I'm gonna say that I don't know because they're unknown. So well, the way you wanna think about it is as follows. First of all, you wanna figure out what you don't know, which means you wanna understand what are the regions of the parameter space that we haven't covered. So back to the plot that I was showing of the phase space of transients. I'm going to turn on my camera, actually, that may be better. Back to the plot that I was showing of the phase space of transients, where you have the magnitude versus the characteristic timescales. There are regions of that diagram that we know we haven't explored. So we want to push LSST to explore those regions first of all. And then it is a very difficult question because a lot of what we do in terms of classification, particularly, as I was saying, LSST will generate information about anything that changes. But that information will be too much for the community to directly access it. So we have to go through brokers that will segregate the classification and direct it to the people of interest. So it's really, the burden is on the people that are writing the brokers to make sure that while they classify things that we know, to give them to the appropriate person for follow-up studies, they also do not bias themselves to throw away everything that they don't know. And it is a very delicate question because a lot of the things, there will be a lot of false positives. There will be a lot of alerts that are not true transients that we don't want to go after. I personally have a dream that the community will develop, will sort of embrace randomness, and I think the best way to deal with the unknown will be to develop a chunk of time for follow-up, for spectroscopic follow-up or photometric follow-up with other telescopes, to entirely randomly selected transients. And most of them will be completely uninteresting, of course. But I think that would be the best way to maximize the possibility of discovering something truly interesting that we haven't thought of at all yet. I don't know if anybody is going to be brave enough to do that.
Okay, thanks. More questions?
Hello?
Hi.
Hi. About the survey strategy, do you expect to have some, whenever you decide, that will be fixed, or that they could be changing through the years?
Right, so they can be changed in a couple of ways. So first of all, there's what's called a rolling strategy, a rolling cadence, which means even though we have to collect, those many images of each portion of the sky to build the static maps. How do we want to do that? Do we need to have a static map for the entire sky in the first year? Can we maybe just completely skip some regions of the sky in the first year and then, sort of segment the sky so that we have a higher cadence every year on a smaller portion of the sky? So, and those questions, that kind of design has to happen, of course, at the beginning of the survey, because you can't start with that and then really change your mind without suffering undersampling in at least one region. But the details of the cadence can be changed as long as the requirements of the wide, fast, and deep survey are fulfilled. So basically, as long as every portion of the sky has maps that are of a certain depth and of a certain resolution. And to some extent, that it has to be changed, right? Because there is stochasticity, there is weather, if nothing else. So the science requirements are specified in the sense of I need a certain magnitude depth at a certain spatial resolution. And that those two things will depend on the quality of the image. And the quality of the image depends on a number of things, including weather. So the very fine details of the survey can be changed, but there are some overarching requirements that have to be fulfilled. So a good survey design from the beginning is, with small changes on top of that, is really what we should shoot for.
Okay. Thank you.
Okay, more questions? So I have another question. Do you have agreements with other telescopes, for example, for supernova follow-up or spectroscopy?
Yeah. So there was recently a study that came out that was done by LSST. Beth Willman, I think, was leading the study on the optical and near-infrared requirements for maximizing LSST follow-up. So as it stands right now, there is no exact contractual obligation yet from the community, but there's a number of surveys that are thinking about how will they support LSST. For example, I did my first postdoc at the Las Cumbres Observatory Global Telescope Network, which is in Santa Barbara, California. Well, that has the headquarters in Santa Barbara, California, but the network is distributed. It's in 7 sites around the world, and it's a completely robotic network of very small telescopes, 1 meter and 2 meter in diameter. But even those can be very helpful in supporting the LSST studies, particularly for the transient sky. Things that are discovered really faint by LSST, but that are changing very rapidly. So so that LSST will saturate on those discoveries very soon. Those can be followed by very small telescopes, by an array of telescopes like LCOGT has it. And the LCOGT telescope is figuring out how to allocate the time, and they have a number of people involved in LSST now to understand how they can best support the LSST survey. The traditional way to do this, of course, is you apply for time and you're a PI of a survey, so you have X number of hours on Gemini, and then PTF discovers something, and you go and observe that something with your spectra. And some of that will happen in LSST time as well. But the scale at which discoveries happen will make that kind of working paradigm prohibitive with LSST. So definitely we need to understand how the community wants to approach the follow-up. There's also discussion of synergy with various surveys like Space Survey, JWST, which is very, very interesting. And we, one can speculate co-observing, for example, so designing the LSST strategy so that it maximizes the overlap between regions of interest for gravitational waves, or JW that it co-observed with JWST, the same region, so that if you do get a gravitational wave, alert, then you have all of your machines the same patch of sky and things like that.
Thanks.
Sure.
More questions? Okay, so I want to thank you again, and thanks everybody for attending, and see you all soon.